Solid sodium reacts with liquid water to form hydrogen gas according to the equation, and the equation is flashed on the screen. What is the pressure in atm of hydrogen gas in the 30-liter headspace of a reactor vessel when 1.86 kilograms of sodium is reacted with excess water at 40 degrees Celsius? So this problem has a two-part solution. The first part would be stoichiometry. The second part will be using the ideal gas law to solve for the pressure. So let's do the first part first, the stoichiometry portion. So in the problem, we are given 1.86 kilograms of sodium. The first thing you need to do is to convert kilograms into grams. So we know that for every 1 kilogram, there are 1,000 grams. So the kilograms of sodium cancels out. Now you have grams of sodium. Next is to convert grams of sodium into moles of sodium. So we will use the molar mass of sodium. And if you look at your periodic table of elements, 1 mole of sodium is equivalent to 22.99 grams of sodium. So the grams of sodium will cancel out. Now you have moles of sodium. And then, using the balanced equation, we will convert moles of sodium into moles of hydrogen gas. And if you look at the balanced equation, you will see the ratio is 2:1. So for every 2 moles of sodium, there's 1 mole of hydrogen gas. So 2:1. So the moles of sodium will cancel out. And this will give you moles of hydrogen gas. So if you solve the equation, so that's 1.86 times 1,000 divided by 1 times 1 divided by 22.99 times 1 divided by 2. And you will get approximately 40.45, and this is moles of hydrogen gas. So this is part 1 of the calculation. This is the stoichiometry part. Now we move on to the second part, which is using ideal gas law. So if you can recall, ideal gas law is given by the equation PV equals nRT. So we are solving for P, or pressure. So what you do is you divide both sides by V, so that V cancels on the left side. So our equation for pressure is nRT over V. Okay? So all we have to do now is to substitute the value. So for N, we have 40.45 moles. For R, we know the value of R. That's 0.0821 liter atmosphere per mole Kelvin. So although it's not given in the problem, this is something you should memorize. For T, the given in the problem is 40 degrees Celsius. But if you remember, whenever you're using ideal gas equation, your temperature must be in Kelvin. So we need to convert 40 degrees Celsius into Kelvin. So if you recall, if you want to convert Celsius to Kelvin, you simply add 273.15. So 40 plus 273.15, what is that equal to? That's equal to 313.15, and this is in Kelvin. So this is the temperature that you are plugging into your ideal gas equation formula. Divided by the volume in the problem is 30 liters. 30.0 liters. So let's look at how the units cancel out. So the moles cancel, liters cancel, Kelvin cancels. So the remaining unit is ATM, which is indeed the unit of pressure. Okay, so our answer is an ATM. So all you have to do now is solve this. So 40.45 times 0.0821 times 313.15 divided by 30, and you should get approximately 34.7 ATM. So the answer to this question is 34.7 ATM.